What if I told you that everything we can see, the stars, the galaxies, you, me, makes up only about 15% of the entire universe? The other 85%, it's a ghost. We call it dark matter. It's all around us, streaming through our bodies this very second, but we can't see it and we can't touch it. So how do you find something that's invisible? Physicists think the answer might lie with a particle so famous it was nicknamed the God particle. Not because it's divine, but because it could be our only real bridge to this hidden reality. The Higgs Boson might be a secret portal, our one way to finally shine a light on the dark. To find our invisible culprit, we first need to get a handle on the crime scene. And the crime, well, it's the fact that all across the cosmos, the universe seems to be flagrantly violating the laws of physics. The evidence for our ghost, dark matter, is overwhelming. It's written in the light of dying stars, etched into the fabric of space-time and stamped onto the baby picture of our universe. Our first clue comes from the majestic, swirling spirals of galaxies. Back in the 1970s, an astronomer named Vera Rubin was studying our galactic next-door neighbor, Andromeda. She was measuring how fast its stars were orbiting the center. Now, logic and gravity tell you something simple. The farther a star is from the bright, dense center, the slower it should move. Think about our solar system. Mercury zips around the sun at an insane speed, while far-out Neptune just plods along. The pull of gravity gets weaker with distance, so things slow down. But that is not what Vera Rubin found. Not at all. To her astonishment, stars at the very edge of Andromeda were moving just as fast as stars near the middle. This was a cosmic scandal. It was like watching a merry-go-round where the horses on the outer rim spun at the same speed as the ones near the center. For that to happen, there had to be a mind-boggling amount of extra mass, some kind of gravitational glue, holding those speedy outer stars in their orbits and keeping them from being flung out into deep space. This mass was completely invisible. It wasn't shining, and it wasn't gas or dust. It was just there. Her observations have been repeated on countless galaxies since, and the result is always the same. It seems almost every galaxy is wrapped in a giant invisible halo of this stuff, which makes up most of its total mass. This was Exhibit A for dark matter. Our second piece of evidence is even bigger, massive clusters of galaxies. Einstein's general relativity tells us that heavy objects warp space-time. Imagine a bowling ball on a trampoline. If you roll a marble nearby, its path gets bent. The same thing happens with light. When light from a distant galaxy travels past a huge galaxy cluster, the cluster's immense gravity bends its path. This is called gravitational lensing, and it can stretch and distort the image of the galaxy behind it into weird arcs and smears. By measuring that distortion, astronomers can do a bit of cosmic accounting. They can figure out exactly how much mass is in that cluster to bend the light so much. And every single time the number they get is shocking. The mass needed to create the lensing effect is 5 to 10 times greater than all the mass from the stars and gas we can actually see. It's like seeing the shadow of a mountain, but only finding a small hill. The only explanation is a colossal amount of matter we can't see, giving itself away only by bending light. This is Exhibit B. Our third, and maybe most powerful clue, comes from the baby picture of the universe, the cosmic microwave background, or CMB. This is the faint glow left over from the Big Bang that fills all of space. About 380,000 years after the Big Bang, the universe cooled down enough for atoms to form and light could finally travel freely. The CMB is a snapshot of that exact moment. When we look at this snapshot, we see that it's almost perfectly uniform, but there are tiny temperature fluctuations like 1 part in 100,000. These tiny hot and cold spots were the seeds of everything. The slightly cooler, denser spots had more gravity and started pulling matter in. Over billions of years, these seeds grew into the galaxies and clusters we see today. And here's the kicker. When physicists run computer simulations of this process, they hit a wall. If the universe only had normal matter, there wasn't enough time or gravitational juice in those tiny fluctuations to build the massive structures we have today. The simulations only match the real world if you add one secret ingredient, a massive scaffolding of some other kind of matter that doesn't interact with light. This stuff would have formed deep gravity wells that normal matter later fell into, eventually lighting up as stars and galaxies. Without dark matter, we wouldn't be here. The universe would just be a boring, featureless soup of gas. All right, so we've got a pretty solid criminal profile. Our culprit is dark. It doesn't interact with light. It's massive, making up about 85% of all the matter in the universe. And its only known trick is gravity. We've already ruled out the usual suspects. It's not just a bunch of dim stars or black holes. Astronomers have looked, and they just don't add up. The conclusion seems inescapable. Dark matter must be made of some new, undiscovered particle. It's a ghost in our cosmic machine, and finding it is one of the biggest challenges in all of science. So how do we find this ghost that's shaping our universe? We need a witness. And our key witness might just be the one thing connected to the only property dark matter consistently gives away. Its mass. That witness, many physicists believe, is the Higgs boson. And to understand why, we need to meet its crew, the standard model of particle physics. Think of the standard model as the periodic table for reality's fundamental parts. It is, and I'm not exaggerating, the most successful and well-tested theory in all of science. It describes every particle we've ever found and every force they use, except for gravity. It has quarks, which build protons and neutrons. It has leptons, like the familiar electron. And it has the force carriers, or bosons, the photon for electromagnetism, the gluons for the strong force, and the W and Z bosons for the weak force. For decades, this model was nearly perfect. But it had one massive, glaring hole. The core equations of the standard model, in their purest form, predicted that every single one of these particles should have zero mass. None, which is obviously wrong. We have mass, planets have mass. And we know from experiments that some particles are incredibly heavy, while others, like the photon, are massless. The theory was missing something huge. Where does mass come from? This is where Peter Higgs and other physicists in the 1960s had a brilliant idea. They proposed that all of space is filled with an invisible energy field, what we now call the Higgs field. You can think of it like a field of thick cosmic snow that permeates everything. The way a particle gets mass is by interacting with this field. Some particles, like the photon, are like skiers. They glide through the Higgs snow effortlessly and have no mass. Other particles are like someone wearing snowshoes. They interact a bit more, sink in, and this stickiness from the field is what we experience as their mass. And then you have particles like the W and Z bosons. They're like someone trying to wade through the snow in heavy boots. They interact very strongly, get bogged down, and are therefore very heavy. You and I have mass because our fundamental building blocks, our quarks and electrons, are constantly sticking to this universal Higgs field. It was a beautiful theory, but for almost 50 years, that's all it was. To prove the field existed, you had to find its particle. Just like the electromagnetic field has the photon, the Higgs field should have a Higgs boson. Finding it meant you had to hit the field, excite it so hard that a little clump of it would pop into existence for a moment. And to do that, humanity built the most powerful machine in history, the Large Hadron Collider, or LHC at CERN. The LHC smashes protons together at nearly the speed of light, creating tiny fireballs of energy that mimic the universe just after the Big Bang. In these collisions, for an impossibly short instant, a Higgs boson can be created. It decays almost immediately, so scientists can't see it directly. Instead, they look for its specific decay signature in the particle debris. On July 4th, 2012, they announced they'd found it. They had discovered the Higgs boson, confirming the Higgs field and completing the standard model. This discovery is what led to the God particle nickname, much to the annoyance of most physicists. The name came from a book by Nobel laureate Leon Lederman. He reportedly wanted to call it the goddamn particle because it was so frustratingly hard to find, but, publishers shortened it. The discovery was one of the greatest scientific feats of our time. But here's the thing about science. Every new answer just unlocks a bigger, better question. And the biggest one was this. If the Higgs field gives mass to every particle we know about, could it also be responsible for the mass of the one thing we know has mass but can't see? Could the Higgs boson be our link to dark matter? The discovery of the Higgs didn't just solve a puzzle. It gave physicists a brand new tool and a tantalizing new idea. The logic is beautifully simple and compelling. We know dark matter has mass. We now know the Higgs field is responsible for giving particles mass. So the most straightforward idea is that dark matter gets its mass from the Higgs field, just like everything else. If that's true, it means there must be some kind of interaction between dark matter and the Higgs field. And if the field can talk to dark matter, then the particle of that field, the Higgs boson, must be able to talk to it too. This theoretical link is what physicists call a portal. The Higgs boson could be a gateway connecting our visible world to the hidden world of the dark sector. This is the core of the Higgs portal model, one of the hottest ideas in physics today. But how on earth do you test for a portal to an invisible world? You look for something that goes missing. You look for an invisible decay. When a Higgs boson is made at the LHC, it decays in a fraction of a second into a shower of lighter particles. The giant detectors are built to see these particles and reconstruct what happened. The Higgs portal theory predicts a new exotic decay. A Higgs boson could decay into a pair of dark matter particles. Since these particles are invisible to our detectors, they'd just fly out without a trace. So how do you detect something that leaves no trace? You use a fundamental law of physics, conservation of momentum. Think of a firework exploding. If half the sparks were invisible, but you saw all the visible ones flying off to the left, you'd know something had to have shot off to the right to balance it out. The same principle applies at the LHC. Before the collision, the momentum is zero, so after, everything has to add up to zero. If the detectors see a bunch of particles recoiling in one direction with nothing on the other side, they can deduce that something invisible carried away the missing momentum. This search for an invisible Higgs decay is a huge deal at the LHC. Now, physicists have to be careful. There's a tiny, well-understood way for the Higgs to vanish, even in the standard model, by decaying into neutrinos, which should happen only about 0.1% of the time. But if the Higgs can decay to dark matter, that invisible rate could be much higher. Finding a rate of invisible decays above that 0.1% would be a revolutionary smoking gun discovery pointing straight at new physics with the Higgs portal as the prime suspect. So what have they found? So far, after sifting through trillions of collisions, neither the ATLAS nor CMS experiments have seen a significant signal. This doesn't kill the theory, but it does let scientists tighten the screws. By knowing how many invisible decays they should have seen, they can set an upper limit. The latest results from ATLAS, for example, say that the Higgs can't decay to invisible particles more than about 10.7% of the time. Another recent analysis places this limit around 15%. This tells us that if a simple Higgs portal exists, the connection can't be too strong. And this is where the search gets really clever, because it links up with another type of experiment entirely, direct detection. These are giant, ultra-pure detectors built deep underground, waiting for a dark matter particle from space to randomly bump into one of their atoms. The same Higgs portal that allows a decay at the LHC would also allow a bump in an underground lab. By combining the non-results from both types of experiments, scientists can corner our suspect from two directions at once. The simple Higgs portal is an elegant idea, but what if nature isn't so simple? What if the dark sector isn't just one lonely particle, but a place just as rich and complicated as our own world, with its own particles and even its own forces? This is the wild idea behind hidden valley models. Imagine our standard model is a bustling, brightly lit valley. Parallel to ours, there might be another valley, a dark valley, shrouded in fog. This valley has its own inhabitants, a whole zoo of dark particles, and maybe even its own forces. It's almost completely cut off from us. But just like before, the Higgs boson could be the secret mountain pass connecting the two. In these theories, a Higgs created at the LHC could decay through the portal into a whole cascade of these new dark particles. This could set off a dark shower where the initial particles radiate and create even more dark particles. Some might be stable, that's our dark matter. But others could be unstable and leak back through a portal into our world, decaying into particles we can see. An event like this would look absolutely bizarre in our detectors. Instead of clean jets of particles, you might see what's called a soft, unclustered energy pattern, or SUEP. Think of a firework that doesn't streak, but instead creates a gentle, spherical burst of hundreds of low-energy sparks. That's what a SUEP might look like, a strange, soft firework of particles with no obvious direction. Another mind-blowing signature could be long-lived particles. What if some of these hidden particles travel for a few centimeters or even a few meters through the detector before they decay? It would create a displaced vertex, a shower of particles appearing out of thin air, completely disconnected from where the protons actually collided. It would be a ghost materializing in the machine. Scientists at the LHC are actively developing new ways to search for these strange, spectacular signals. These hidden valley models open up a whole new playbook. The search is no longer just about what's missing, but about finding positive, if profoundly weird, signs of a new reality hiding just out of sight. This is the absolute cutting edge of physics, pushing the boundaries of what we can even imagine. If you think this stuff is as cool as I do, consider subscribing and hitting that bell so you don't miss our next exploration into the unknown. So, back to our big question. Could the Higgs boson really be our guide to dark matter? The journey we've taken paints a compelling, if not yet complete, picture. We started at a cosmic crime scene where 85% of the matter is missing. We met our key witness, the Higgs boson, whose entire job is to deal with mass. We saw how the Higgs portal theory gives scientists a prime target at the LHC, a search for missing energy that signals an invisible decay. While we haven't found it yet, the search has put tight constraints on the simplest ideas. We even journeyed into the wilder hidden valley models, where a Higgs decay could unleash spectacular and strange signatures in our detectors. Let's be clear, as of right now, we have not found that portal. This is the life of a scientist on the frontier. It's a careful process of searching, ruling things out, and slowly tightening the net. And the hunt is far from over. The Large Hadron Collider is being upgraded to the High Luminosity LHC, a project that will crank up the collision rate dramatically. It will produce billions of Higgs bosons, giving us an unprecedented chance to spot incredibly rare decays that might be hiding just beyond what we can currently see. The discovery of the Higgs in 2012 wasn't the final chapter. It was the beginning of a new era. It wasn't just the capstone on our theory of the visible world. It may have handed us the only key we have to unlock the other, much larger universe that's been hiding in plain sight all along. The search continues, and with every collision, we get one step closer to finally shining a light into the dark.